The motivation for this talk I'll present, I'll kind of go over what we already know about Greenland and why it's difficult to separate present-day ice mass signals from the GIA signal using satellites and other observations. And then I'll kind of talk about the theory, how can we use GPS and absolute gravity together to solve this problem. Finally, I'll discuss the field experiment and what this means for Southeast Greenland. I have 53 slides. Now, the reason I show you that I have 53 slides is not to freak you out. I talk very, very quickly, so this should be over in 40 minutes. But sometimes when I'm sitting in a talk that I don't enjoy, knowing how many more slides are left makes me feel better. All right, let's get straight to it. The motivation. This is a picture of the temperature of the Earth starting back in the late 1800s. And since then, it's risen by close to 1 degree centigrade. And most of this rise has been attributed to atmospheric greenhouse gases. Now, if you read the literature, this is a very, very robust signal. You can look at what is on the continents, you can look at what's in the oceans, you can look everywhere, you can filter out heat spots, and this is a robust signal. So we believe it. And you see that it's continuing to increase past the median. What happens when the Earth's temperature rises? Well, of course, we'll have a sea level rise. First thing that happens is that temperature rises, and the water in the ocean also rises. And this is due to two things: the thermal expansion of the water itself, the surface water, and that accounts for about 50% of the sea level rise that we see. And then we also have just the change in state of the ice on Greenland into water in the ocean. So it's like filling up a cup. This is a picture or a graphic from the Intergovernmental Panel on Climate Change from the 2014 report. And these are 5 different models here that predict how sea level is going to rise in the future based on different global warming scenarios. And each of the colors of the, let's see, get this right, of these things down here represents a component of the sea level rise system. So we have thermal expansion in red and continental glaciers, Greenland and Antarctica. Greenland is in green, as you can see here. And what you see on this plot is that after the thermal expansion of the oceans and after the melting of the continental glaciers, Greenland is the 3rd most important component of the sea level rise system. All right, now to give us some context of place, this is what would happen if sea level rose by, if all of Greenland melted, it would cause sea level to rise by 6 to 7 meters, and just shows you what's happening here in terms of what parts of the coast will be flooded. All right, now we have Brussels will be okay, Paris will be okay, but Antwerp is going to be a mess. And the problem isn't so much that all of Greenland has to be a mess, but this sea level rise is accompanied by an increased threat of flooding because the surface of the ocean becomes warmer, and because we have more threat of flooding, more threat of storms, more threats from hurricanes, which are a problem as you get closer to the equator. Now, we can't change what's going to happen. The temperature is rising, and it's probably very late to try and turn it around in the next few decades. So we can't do anything about that, but we can prepare for the effects of this sea level rise by trying to understand what precisely is happening in Greenland and to model it very, very accurately. So what we need from Greenland is we need to know the mass loss. It's not sufficient to know how the surface is changing. We need to know how the mass of the ice is being converted into volume into the oceans. Okay. The decline of the Greenland ice sheet is very, very well known. I'm just showing this, but there are there's lots of evidence, and I'll get to some of those later, that show how Greenland is melting. This scale at the bottom is in, all right, I'm doing something wrong, but, oh, I know, push the button. All right, down here is happening up here, and you see that the mass loss isn't consistent over the whole ice sheet. We have hot spots here where there's a big outlet glacier. There's a big outlet glacier over here that's starting to show evidence that it's starting to slide really big. Up here is Petermann. Petermann Glacier was in the news recently because big pieces of iceberg have broken off. And then I'm particularly looking at this place down here. This is the mass loss curve from Grace, and you see it's not a linear change. What's happening is that there are accelerations over those 20 years of observations. And sadly, this year it died, or 2017 it died, so no more Grace. And we have to find other ways to bring the model or the records from Grace, tie those to a new satellite observation that will probably start in 2019. All right, how long would it take for Greenland to melt? Well, if we take an ice mass, a loss rate from about 2006, and we take the volume of ice in Greenland, it should take about 13,000 years. But predictions indicate already that today, the rate that we're seeing today should double by 2020. That's only 3 years away. And then there are positive feedbacks in the system as well. So as the ice melts, there's less albedo, which means that instead of reflecting, Greenland gets warmer and it melts faster and faster and faster. And again, we go back to this idea that it's not so much that Greenland has to melt entirely, because even small changes in Greenland melting will affect coastal communities around the world, and a lot of them are not in democracies or capital countries where they have resources. So this is a reason why we need to understand what's happening and see if there's anything we can do to support these coastal communities. We do know a lot already about the Greenland ice melt, and most of our observations come from airborne laser altimetry that started in the mid-1990s. Satellite altimetry, there have been 2 altimetry satellites, ICESat and then Cryosat-2, was in 2003, and then satellite imagery, of course, is showing us how the glaciers are changing really quickly. Now, I don't know how much you guys know about altimetry, so forgive me if I'm being too elementary for you all, but the way airborne laser works is a plane flies over the Greenland ice sheet at one time, okay, and it measures the distance between the airplane. Well, we know where the airplane is with respect to the center of the Earth because of GPS. And then the airplane comes back 10 years later, X number of years later, flies again, and we get a new surface. And then we take that delta T here, and then we divide it by the change in the surface height, and then we'll get a change in rates of mass loss. Maybe. The same thing happens with satellite altimetry. Satellites fly. They tend to have more regular crossover times where they come back more regularly, so we can get better, more dense information from satellite altimetry. But the idea is it measures the height of a surface once, and then it comes back and measures the height of the surface again. So this is a picture of the topographic mapper flights that were taken by NASA between 2013 and 2014, and you see how sparse they are. But they have focused on places where there are big outlet glaciers, because we need to understand how this is changing the most. And here's just one example of how the elevation of the Jakobshavn drainage basin, that's in this part of Greenland, has changed over time. So it's dropped by, about 10 meters over that time period, from the mid-1990s to early 2012. Okay? Now, this is a picture of what we get from satellite altimetry, and this is a picture, again, it shows that there's a lot of ice mass loss. It's particularly focused at where the outlet glaciers are along the edges of Greenland. The other thing that's important to note is that these outlet glaciers are glaciers that float in the ocean. Down here, these are all land-terminating glaciers. So these are speeding up, we think, because the ocean is warming up. So they're melting from below, and they're sliding out into the ocean. And that's caused a lot of speed up in the mass loss of the Greenland ice sheet. And then here's another picture using Cryosat-2, which has only been flying since 2011. Again, highlights the outlet glaciers, but it's also showing a lot more inland information than we had before. And then I mentioned imagery, INSAR, Landsat. This is a picture of the Jakobshavn Glacier. It's the big glacier that's on the west coast of Greenland, right about in the middle, and I'll show you on a map. Now, this is where the front of the glacier was in 1851, and this is where it was in 2009. There's a story by some colleagues of mine who, I don't know when they went, but they went 5 years later again to do some observations there in the front. Front of the glacier wasn't where it was supposed to be. In fact, it was 12 kilometers back from where they expected it to be. So it's been moving really, really fast. And the Landsat images, of course, are these colored images here, and these are based on human observations. All right. Now, this is all great. Why can't we just use those numbers to estimate what's going to happen with sea level rise? Well, these remote sensing techniques give us volume change. And what we need to estimate what's happening in the oceans is we need a mass change. And so we need to understand what is the density of ice. The density of ice that we need to multiply by this volume change to estimate a sea level rise. You'd think that would be very easy, but in fact it isn't. At the top of the ice, it has snow has a density of about 50 to 70 kilograms per meter cubed. You go down 80 meters. Somewhere here, well, where is it? 80 meters, right there. And it's gone up to 830 kilograms per meter cubed. And then you go down even further, so down here, below 160 meters, it's approaching what we consider the density of ice, 917 kilograms per meter cubed. So it's not so straightforward. We can't just say, oh, we lost a meter of ice this year, so let's multiply it by this value of 917. It's much more complicated than it should be. And old ice versus new ice, blah, blah, blah. It's a very complicated. So it's not a straightforward estimation of what the ice mass is actually lost. So those techniques that I showed you up to now, they just give us volume changes. GRACE came along in 2002, and it was measuring gravity. It was measuring gravity, which could be converted directly into a mass change. And that was going to solve all of our problems, but I hope what you guys are thinking in your head, that even changes in a GIA signal is a mass signal. And so GRACE is measuring what's happening today, but it's also measuring what's happened in the past, the response to the Pleistocene melting of the glaciers. And there are a couple of other problems with GRACE. Is the size of the footprint. The best we can do now is a footprint of maybe 350 kilometers in radius. We still have uncertainties in the background models. We think we're doing pretty well with those, but if there's a linear trend in those background models that we don't understand, then that can go into what we're predicting for the ice mass change. And then we get these changes in gravity that need to be converted to changes in mass. And we know that gravity changes not just because of the melting of the ice today, but also for the glacial isostatic adjustment signal. And that represents, depending on where you are in Greenland, up to 30% of the signal that GRACE is seeing. So this is a picture, and it shows you why we can't just model glacial isostatic adjustment. To measure GIA or to estimate GIA, you need geologic evidence that goes back about 5,000 years. Now, we have places in the Pacific Ocean that we can use. We can use corals there. We have places in the United States in the Great Lakes that we can use and get really good signals there. Now, what I'm showing you here is a single model that assumes heterogeneity of the mantle and a certain ice load history. And you see that here Greenland is supposed to be uplifting from GIA, and this is what you would expect. The ice melts, you expect the Earth to rebound up, but there are other places where it should be subsiding because of GIA. And one thing I really want you to notice is this area right in here. It has a tiny, tiny negative signal. I said it's positive, but in fact it's negative in the southeast. This is the crux of my presentation, is that we find that it's positive, and no matter which models you use, which ice melt models you use, which earth mantle models you use, which viscosity you use, there's hardly any way to get this to be a positive value. We expect it to be positive, ice is melting, mantle is coming back in, and so the Earth should be going up, and that's not what these models predict. So, This talk is about using geodetic techniques, absolute gravity, and in this talk I only use the uplift part of the GPS data. And we rely on elastic loading theory. It makes sense. The surface displacement is proportional to the surface mass load, and this will give us mass directly, okay? So how does this work? Let's say we have a pinned elastic band. Let's go to the most simple kind of Green's functions we've ever heard about. We know the properties of that elastic band really, really well. If we apply a point load at a certain point along that between that band, we'll get a displacement. And a Green's function tells us, no matter where we are along, if we know the load, if we know the elastic properties, and we know where we are on this string, this band here, it will tell us how much the displacement is. And if you have loads at many places, then all of them will sum up linearly to give you the displacement at a single place. I hope that's clear. It's actually much simpler than the way I've probably explained it. So we can take that simple two-dimensional model and also apply it to the Earth. We know the elastic Earth properties reasonably well from seismology, and so if we apply a known load at the surface, then we should be able to predict the surface displacement at any point at any distance from the single load itself. Oops, God, I'm a klutz. All right, how does this work? GPS is on the surface of the Earth. We apply a load to the surface of the Earth. It causes the surface to displace, and we can measure how much it's displaced. The GPS receiver will move down and toward a positive load on the surface of the Earth. So likewise, like we'd expect to see in Greenland, we remove a load, and then the GPS at the edges of the ice sheet will move up and move away from the center of the ice sheet. Now we can also turn this around and think of it not as a forward modeling problem, but as a problem of inversion. If we put GPS around at certain places in the world, let's say around the Amazon basin, and we can measure how much mass change there is in the Amazon basin from one season to the next season, we can forward predict what the GPS positions will do. Now, if we place GPS stations around the Amazon and we see that they're changing up and down, moving up and down, we can invert that information to give us the mass change of water in the Amazon basin. So in a forward sense, we've been doing this for decades. This is a signal of the GPS in Potsdam. This is one of the best signals. And then this is the predicted uplift from a water storage model over a global water storage model. And you see the annual signal is reproduced really, really well. And so just shows that this works to first order at least. And the idea then is let's put GPS receivers on bedrock around the coast of Greenland. We measure for a decade. They're moving up and away, and we should be able to invert these data for the mass loss change in Greenland directly. But we still have a problem. As with GRACE, GPS is also measuring glacial isostatic adjustment. So we have to be able to separate these two signals in our GPS signal. It turns out that you can't just use GPS alone to separate the signals. There's a theory that allows us to combine GPS with absolute gravity that allows us to separate GIA from the present day, from the signal that would be due to present day melting. Okay, so now I'm going to jump into the theory. You see, I'm already at slide 35. There was a paper written by my thesis advisor, John Warr, and a couple of his PhD students back in 1995. And he showed in this paper that if you measure gravity and absolute gravity and GPS simultaneously, then you can solve for the GIA signal. The problem with this technique is that it's not a long wavelength technique as GRACE, but it can provide observations and information that no other technique can. And so we don't see this as a technique that works all by itself, but as we assimilate lots of different kinds of information to come up with a conclusion this is another set of observation that allows us to constrain the problem a little bit better. How does this work? Okay, for those of you who are not interested in math, this will only be about 30 seconds of pain. All right, so we know, as I've said, the uplift at the edge of Greenland is due to a signal due to GIA and a signal due to the present day mass loss. I'm sorry this didn't come out well. These are supposed to be subscripts. And the same thing with gravity. We measure gravity at the edge of the ice sheet. What we're going to see is a change in gravity that's due to the GIA signal, but also the present day ice mass. To make this derivation a little bit clearer for everybody, forget the dg dt, and let's just assume that these variables here stand for rates, okay? So uplift is due to GIA and ice, gravity is due to GIA and ice, but remember, gravity changes not just because of uplift, it also changes because of mass, and we know this free air gravity correction from theory, and so we can put this back into the equation. And then the paper from John Moore showed that the change in gravity due to GIA has a ratio of 1/6.5 to the change in uplift due to GIA, okay? So now we're still stuck at this point with trying to figure out which one has the GIA signal in it. We do some substitutions, and we come up with this equation here, that the gravity in GIA is related to the free air gravity change times the uplift plus this ratio due to the GIA part. And this gives us a relationship, again, between the GIA signals in gravity and uplift. And if we can find a relationship between the elastic components of gravity and uplift, then we can eliminate these from the equation, and we can pull out GIA directly. Now, it sort of sounds like we need to know what the mass change is first, but if you think about elastic loading, it's a long wavelength signal. You have to have a signal, either a very, very big signal that's very small, covers a very small area, or you have to have a medium signal over a very large area to cause a change in the surface. And so, So, in fact, we don't have exactly what's happening in Greenland today, but we have some models that allow us to kind of work through plausible estimates of what is the relationship, what is going to be the relationship of elastic gravity to elastic uplift. And that's what this paper that came out last year was all about. And this actually goes into it in a lot of detail, and probably too much detail than what you guys are interested in. But if you're interested, I can send you that paper and even my talk. So now let's go on to the observations that we use to validate this theory and to get an estimate for glacial isostatic adjustment in Kulusuk, which is in the southeast corner of Greenland. We started our experiment back in 1995, and we were supported by NASA and by the National Oceanographic and Atmospheric Administration to install a site here. So in 1995, we went in, we installed the GPS receiver there. It was the second permanent GPS receiver. The first had been installed by the military up in Tuli. And then the next year, in 1996, we installed permanent GPS, and absolute gravity. We went there and took absolute gravity in 1996 in Kulusuk. So this is the area of the map that I'm going to be focusing on. Now, before we started this experiment, we wanted to look at the errors on our signals and decide how long this experiment would take. And if we assume that we have daily GPS observations with the best precision that we have now, it would take 3.5 to 4.5 years to get a decent trend on the GPS, including the annual seasonal or the seasonal signal. With annual absolute gravity observations, we know it has a precision of about 1 microgal. It would take 1 microgal per year. It would take a decade to obtain the required precision to separate these two signals out. We didn't tell NASA that when we went into this, and we've been able to find additional support as we went along. If they knew that it would take a decade, they would have never given us the money in the beginning to do it. But because they gave us that money in the beginning, we were able to find more money, and now we finally have a result. I don't know how many of you have seen the FG5 absolute gravimeter. This is the latest generation with a transparent dropping chamber. It observes the free fall of a corner cube, okay? It uses lasers as the length standard, and it uses a rubidium atomic clock as the time standard, and we get a precision of 1 microgal, or about 1 part in 10 to the 9th, and it's it's measuring the free fall of the corner cube, little g, wherever we set it up. The instrument can detect a free air gravity correction of about 3 millimeters. It turns out that a euro is a little bit smaller than 3 millimeters, but a British pound is about 3 millimeters. So if you put a British pound under each of those feet, then you'll detect a change in gravity. So it's an extremely sensitive instrument. Now, forget all of those professors that have told you never put a lot of numbers in a table that you want people to read. This is just to demonstrate to you what our gravity observation field work has been like. So this is Ilulissat, this is Kellyville, this is Nuuk is down here. I'm not sure what this is. Quakertalk. No, Quakertalk is down here, Nuuk's here, and this is Kellyville over here. And so since 1995, these are the observations we've taken. And I'm only going to report on these here from Kulusuk. So let's look at the results from our absolute gravity observations. Oh, I wanted to tell you that every time we go to Greenland, it costs about $20,000. The equipment, the FG5 absolute gravimeter, weighs about 500 kilograms. We have to carry a tent, we have to carry a heater, we have to carry a generator, all of these sorts of things. So getting the cargo to Greenland costs about $20,000 a year. And if we do, we can do for $20,000 maybe a couple of sites per year. So that's why it's a little bit sparser than we'd like it to look like. Another reason to look at Kulusuk over here is that there's no geologic evidence. For some reason, this is one of the parts of Greenland where there's no geologic evidence. Every time the glaciers come through, every time something builds up, we've had little ice ages, we've had other events, it just wipes out any of the history from the Pleistocene glaciers. So there's no other way to get glacial isostatic adjustment signal using shorelines or other marks in the sediments or the rocks there. You can't do it. This is the only way to do it, that people have been able to do it. So here are our observations. GPS observations are these black lines here. Most of the time it was daily. And you see down in here in the beginning we had lots of problems. We had antennas blow off. It's an incredibly difficult site, even though there's an airport there, which is why we chose it. So the first thing you could see is this traditional hockey stick that everybody sees in Greenland, that from 1995 to about 2003, everything looks okay. And we expected it to continue with this trend for a decade so that we could solve the problem. And then boom, 2003, there was an increase in melting. 2010, another acceleration in the melting in Greenland. And I think if we look for the last, there's been an effect due to the clouds, clear skies over Greenland, that are making it go even faster. Now these red dots here, these are our gravity observations, and they've been converted to something you can compare with the uplift using the free air gravity gradient. One thing to notice about the absolute gravity is that we have these 2 points out here, and then everything else seems to kind of work together after that. The first thing that happened is that when we started this experiment in 1996, this hotel didn't exist. And by the way, this is where that's the GPS site there, and we'll install the absolute gravimeter right beside it in a tent. So after this hotel was built, it was built in 1997, it caused gravity to change. The hotel pulled the gravity of the area down by a little bit. So we cannot, without reconstructing this model extremely, extremely well, we've just had to throw out these 2 expensive data points. The other thing I'd like you to notice about the gravity also is that here the gravity seems to match really well, but with time you see that the gravity starts to diverge from the GPS signal, and that is because of the GIA signal in the data. So this just shows you we are going to be able to see GIA. Now, when we started this experiment, we really just expected to see a nice linear trend in all of these places, in the gravity and in the GPS data, and that's clearly not what we see. So the best way to deal with this data and to be as honest as possible and transparent with our analysis is to break up the GPS data into these two sections of data. We clearly have one trend here and one trend here, and that's what we've done. So using our models that are outlined in the paper, we calculate absolute gravity and gravity trends for these periods here. Okay, so 1998 to 2003, 2003 to 2012, 2003 to 2015, where we have data. Absolute gravity, it doesn't matter that they don't match, because there have been accelerations in the melting of Greenland. Same thing over here. They don't match up, and you see that the uplift is getting much, much faster. But these are the estimates for glacial isostatic adjustment. In the beginning, it's very big. Then for this long period here, it's a moderate level, and then boom, when we include 2015, 3 extra years of data, it starts to match this number up here. Now, if we take a weighted average of that data, we get a positive signal. So what's important about this is that all of the models, no matter which ice model you use, no matter what mental model you use, they all predict that GIA in this region is going to be negative. And this is the only evidence at all that shows that it's positive. So you should be asking yourselves, well, what are you doing that's so special? Why would it be positive? Well, it should be positive because it's a rebound signal we're trying to measure. But there's also, this is the plot that shows the different models. So this is a model with ice 5G, minus 1.7, minus 1.5 with a different viscosity model, minus 0.7 with the heterogeneous model from John War and Garou there. So why are we seeing something different? Well, why we're seeing something different is due to this hotspot trace here. So Greenland is attached to the North American plate. When the Atlantic is opening, it passed over a hotspot. And the hotspot track starts over here where Jakobshavn is to where Kulusuk exists today. And so we think that there's still some residual heat in the mantle, making the mantle much less viscous than most of those models predict, and that's why we're seeing the positive signal in GIA in that location. So I'm already at the summary. 53 slides. So we know global warming is happening and it's causing sea level to rise. Greenland melting is one of the biggest contributors to sea level rise. And we know we can't stop sea level rise, but certainly having a better understanding, better observations, and a better quantification of what's happening in Greenland will allow us to predict where and how fast sea level is going to rise. GPS and gravity, this is what this talk is all about, at Kulusuk were used to determine the GIA signal there. And we find that the GIA signal is positive, and this is probably because the mantle is hotter there due to the hotspot trace. This GIA signal accounts for about 50% of the uplift signal that we see in Kulusuk. That's a really big number. And there's no other way to get this signal from this region. You will dream that sentence. There's no other way to get this from this region. And so this is a way, this is a really neat way to calculate GIA when we have absolute gravity. But absolute gravity isn't something you carry around in your suitcase. This experiment took 22 years to get this information at a reliable level. Our single GIA trend at Kulusuk, I don't want to oversell it. It's still a local observation, but it does mean that we can use this observation to improve our models of ice mass change and the mantle viscosity in this region. So that's valuable. It's not going to tell us, we're not going to be able to extrapolate this number to the entire ice sheet and be able to extract the present day signal. But it does mean that in that location, we can also get an elastic displacement signal. And this in situ observation can be used to constrain observations that are taken from GRACE and other techniques. So this improved estimate of elastic uplift can be used to test new ice mass change models, thus getting us to the place where we can predict sea level a lot better than we have in the past. So that's all I have for you. I can't believe that I did it that quickly. But I'm here. I'm sorry I missed the 9:30 thing. If you have questions, please.
It would affect your result. Hello?
Yeah.
Did you hear me?
Yeah. So I think, based on what we see, I think that we have only 20 years of observations, and I think it's fairly safe to assume that over those 20 years, that the viscoelastic signal is going to be constant over that time. That's the thing that allows us to do this kind of work, is that GIA has to be constant over that time period. And I think it is constant over time periods of 100 years or so. That really big changes in the mass have to happen before the Earth has time to start kicking in, responding to it. Does that answer your question?
Yeah, but no, I'm wondering about the current melting. Is there any possibility of viscoelasticity in the Earth's response?
No.
After 20 years?
No. If you look at the response of the Earth, we have viscoelasticity at seismic frequencies, and then it's all elastic up to 10 or 100 years response time.
Yeah, but from post-seismicity, for example, we have a viscoelasticity with a very short time wavelength, so maybe, I don't know. Okay. It's the same question.
Okay. We don't need a microphone.
Do you assume that the lithosphere or crust is under tension or compression, or is it assumed to be unconnected? And if the crust was under tension, would that change how it responds to the load?
We don't make any assumption about that in our theory. The Green's function theory that was derived by Farrell back in 1972 takes in just the rheological properties. It doesn't take into account any surface tension, except for the fact that stuff isn't flying off into space. So there has to be gravitational attraction at the center. But no, there's nothing assumed as an interaction in the horizontal.
Concerning the GIA models, I thought perhaps the problem not coming mainly from the viscosity in that case, but that the pattern of ice over Greenland in the past was really not well constrained. So how robust is the idea that the sign is influenced by a hotspot, by the hotspot lowering the viscosity there? Could it be just the fact that our ice models are bad?
No. We have tested as many ice models as are available, and they're coherent over very long wavelengths. So the hotspot trace is much more confined in space, okay? So the other models are coherent over space. The hotspot is very, very fine, and this is something we feel is a very, very robust result. There was a paper by Abbas Khan, and I'm on that paper, and it's from, I think it was from 2016, and it discusses the problem quite well.
Yes, so you say that Greenland is melting, but on several of your maps of the ice thickness changes, so it's possible to see that the ice is indeed melting on the periphery of the continent, but it seems to be thickening in the interior of of Greenland. So does it mean that the overall balance of the ice mass is decreasing, or it's just a difference in the geography of and that most of the melting occurs in the periphery of the?
Well, I think if we go back to, just a second. If we go back to the Grace figure here, for example, excuse me, since 2002, you see that it's not actually, if it's thickening very slowly. So here it's either not changing, it's between 0 and maybe gaining a half gigaton per year, or half a meter of water per year. So I think that the error bar on this
so really
is probably as big as the signal itself. If this were 4 meters, well then I'd say yes, that your conclusion is perhaps right, that everything is in equilibrium. But the fact that we're seeing this picture, this very, very long wavelength coherent picture from Grace, and then there's other evidence from the altimetry as well as from the spectral imaging, it's just boom, boom, boom. Everything is showing us that it's not in balance. There are some really good papers by Reitbrock, Michel Reitbrock on this subject. If you're interested.
Please, I didn't really catch why the estimate of the GIA in the period 2003-2012 was much lower than the 2 other estimates in Kourou.
Because of the observations, the noisiness of the observations. What I showed you is the entire time series, and if first look at this time series from here. Sorry. If you look at this time series and you try and fit a trend to it, you see that it's probably more like a quadratic, and then something else, another acceleration happens here. So when I showed you mine, we were just fitting lines to this to try and do our best to do a line. We haven't tried to fit a quadratic to see if that would change the results. So if we do the period between 2003 to about 2012, you see that there's another slowing down here, and then it starts up again. So that chunk of data, I think, there's a lot more variability in the observations and in what's happening than we actually take into account in our observations. This is a first order assessment of what's going on. And I don't know how valid it would be to take it to higher orders. So that's why there are the error bars as well. And all of the GIA's observations agree to within the error bars.
Since you're on that slide, I have a question myself.
Yes.
So you mentioned the hotel, which was built in 1998. No, just stay to the
Okay,
slide.
yeah.
So which is why you say there's a jump in the gravity data.
Yeah.
But I isn't it clear to me why building the hotel is making the data better consistent with the GPS data, or is it just that it's a relative when you convert your absolute gravity data into the units on the left, which I guess is something like millimeters or something like that?
Exactly.
Are you free to move things up and down for the
That's
record?
exactly what we do, is we find the mean of the gravity and fit it to the mean of the GPS for the whole time period. So these are just outliers based on this set of observations. They're outliers because of the change in mass, local mass.
Sure. But then what about the other outliers?
No, those aren't outliers. This is completely consistent. We know that in the area where we're working, it's Greenland. There's not a lot that goes on there. There's no construction. There's nothing going on there. So we know that there have been no big mass changes related to people since we've started our observations since these observations in 1998. So we know this is caused by the mass, and that this splitting up of the signal is the GIA effect in these two observations.
D'autres questions? Non? Sûr? Ok. Je vous rappelle que vous êtes invité à déjeuner avec Tonie, là tout de suite, dans la médiathèque. Hein. Il y a des plats qui vous attendent. So, thank you very much.
Thank you all very much.